So I had told you a while ago that I was going to ask you to, that one of the problems on the final is going to be derive the wave equation. So I thought I would just quickly run through that again, starting with Maxwell's equations. And Maxwell's equations, together with this identity, by the way, these things, I posted a kind of one-page summary of everything that comes into, everything that we've learned about electric and magnetic fields on SmartSite. I'll also post, actually it may be on one of the finals, but maybe not. I'll post what your final will have as an equation sheet on the back. So your last page of your final will have an equation sheet. So I'll post that on SmartSite too, so you know what that is. But it'll have these Gauss's laws in differential form. So differential form is another way of saying local form. It only depends on what's going on at a point. Well, and how things are changing at that point. And so I'm either going to ask you to derive a wave equation from Maxwell's equations for the electric field or for the magnetic field. You can do either. Not you can do either on the final. I'll ask you to do one, and you'll have to do that one. But it's possible to do it either way. And so I think what I did before was for an electric field, so let's do one for the magnetic field. If I want a wave equation for the magnetic field, then I'm going to try to end up with nothing but B in the equation. So I'm going to need to get rid of E somehow. Get rid of all the electric field parts and only have the magnetic field left. And if you look at the way to start on either of these is to look at Ampere's law and Faraday's law, because they have both. They have both B and E in them. If I wanted to get rid of B, for instance, I don't because I want to do the one for B, but suppose I wanted to do the one for E, and I wanted to get rid of B, then if I took the curl of both sides of Faraday's law, I'd have a complicated thing on the left, and I'd have the curl of B on the right. And the curl of B is something that I can look up here at Ampere's law and say, wow, that's something I could stick right in there, and there will only be E in the equation. So that would be the first step you might take for the wave equation for E. I'm going to do the wave equation for B, so I want to get rid of E. So I'm going to take the curl of Ampere's law. Ampere's law says that the curl of B depends on the current density, current per unit area, and it depends on E. So if I really wanted to write it out, I'd do that. I'm going to switch derivatives here between the spatial derivative. This curl is a bunch of spatial derivatives, so I swap the spatial and the time derivatives. That's essentially always okay to do. So now I have something that has the curl of E on the right, and I can replace the curl of E with something that depends on B. So then I'll just have B. Now I also have J sitting here, and so because this is free, this says a wave equation in free space. Because this is free space, J equals 0 in free space. There are no currents in free space. Because there are no currents, this term is 0, and so what I end up with del cross B is mu 0 E0 partial t of del cross E. But I can look here at Faraday's law. Del cross E is minus partial B partial t. So now I have something that just has B in it. And so I just need to show that that's a wave equation. And the way I'm going to do that is this. First of all, the right-hand side has a second derivative of B with respect to t. That's already a piece of the wave equation. So what I need is a second derivative, a spatial derivative on the left side. What I have is this mess right here, del cross B. And we're just going to use this identity, which you probably saw in Math 21. A cross B cross C is that. The standard mnemonic for that is back cab. B minus B A dot C minus C A dot B. So that's what I have here. When you think of A dot B as vectors, ordinarily you would say A dot B equals B dot A. I mean, dot product is commutative. But del cross B doesn't equal B cross del. I have to have all of the derivatives on the left side. They have to be taking the derivative of something. So in using this, all you have to do, what you want to do is make sure that the derivatives stay on the left. Back is BA, and that's these two, so that's already on the left. If I just use the first part of that, the second part has B here and then del dot del. So the way to make sure the derivatives go where they belong is to move this A dot B over to the left of C rather than to the right. On one of the videos that I posted on the web, I went through this not in terms of this identity, but in terms of let's write out this whole thing in gory detail, and you'll see that it works out this way. So, Gauss's law for magnetic fields tells me that del dot, the divergence of B is 0. Because there are no magnetic charges, B never diverges from a point, is what that's telling you. And so all I have is usually written as del squared of B. And I got two derivatives of B over here. So let's throw away the 0. That's the wave equation. Two spatial derivatives. You might say, what is this? What is a gradient dotted with a gradient? If you remember, this gradient basically is 3 pieces. The x piece is partial x. The y piece is partial with respect to y. The z piece is partial with respect to z. So when you take a dot product of those two gradients, you end up with what you would expect from a dot product, which is 2 of these, second derivative with respect to x, plus second derivative with respect to y, plus second derivative with respect to z, and all those derivatives are derivatives of the b vector. So this wave equation is a wave equation where b is a vector. So you just have to remember, if you're actually using this, that this really represents, this single wave equation really represents 3 wave equations, one for each component of b. So there's an x wave equation, a y wave equation, and a z wave equation. But that is it. So I just thought I would go over that quickly. Any questions on that? So I'm either going to ask you to derive the wave equation for B or the wave equation for E, one or the other. By the way, these two constants equal 1 over the speed of light squared. Usually the speed of light is, you would use the word C, the letter C. I'm going to use V here just to remind you that this is a normal wave moving with a velocity, with a speed V.
Question? Why did you say the first one was 0 again?
Why is this one 0?
Yeah.
The divergence is 0 because of this Gauss's law.
Oh, okay.
And so for the E, if you're doing this for E, you also find out that del dot E is 0. But that's not always true. That's only true in free space when there's no charges. Because this rho here is the charge density, charge per unit volume. So in free space, del dot E, the divergence of E, is also 0. And you end up doing the same thing, throwing the same thing away. So, any questions? Yeah.
Can we simply cancel out the negative sign?
Pardon me?
Can we cancel out the negative sign?
You know, I'm just sitting here wondering about the negative sign now because yeah. I mean, there's a negative sign on both sides. I was just a little worried about it, but in fact, both of them are 2 derivatives of a cosine function, so both of them are going to bring down an extra negative sign. You do cancel out the negative sign. Yeah, I didn't throw them away, but I should. I mean, after I throw everything else away, I can throw away those negative signs, and then I have a wave equation. Yeah. Yeah.
If this was for E, would it be the same except for E?
If it was for E, it would be exactly the same, except the B would be E. That's right. It works out exactly the same. They're both wave equations. Both of them behave like a wave. If you pick and you could go through this, but I'm not going to ask you to do it. It's just a bunch of derivatives, a few derivatives. If you take E to be along the x direction, say, and the wave to propagate along z, then you'll find out from the equations that B is oscillating perpendicular to that. You also find out from again, I'm not going to ask you to do this, so I'm not going to go through it. You also find out from the fact that in free space, the divergence of E is 0. You find out from that Gauss's law or Gauss's law for magnetic fields that the oscillating part of the field has to be perpendicular to the direction of travel. So you find out that it's a transverse wave by using one of those two Gauss's laws.